A linear homogeneous equation looks something like this. We have a function times y double prime plus another function y prime plus yet another function y is equal to 0. Now if we replaced the 0 with some function consisting of only an independent variable, x or t, whatever have you, you will get a non-homogeneous equation. But for now, I'm going to deal with only homogeneous equations and the ones for which a, b, and c are constants. So if they're constants, I have a y double prime plus b y prime plus c y is equal to 0. Our solution to this is always assumed to be of the form y is equal to e to the power rx. Now if I take the derivative of this y prime, I will get r e to the power rx. And if I differentiate this again, I will get r squared e to the power rx. Now I said that this is a solution to this equation. So if I substitute this, and this for this, and this, what do I get? I will get ar squared e to the power rx plus br e to the power rx plus c e to the power rx is equal to 0. Now I can factor out all of these e to the power rx's. Then I will get ar squared plus br plus c equals 0. Now e to the power anything never goes to 0. So I can divide this whole thing by e to the power rx. Then I'm left with ar squared plus br plus c equals 0. And this is what we call as the characteristic equation for solving second order homogeneous equations with constant coefficients. Now if you solve this, you will get two roots, namely r1 and r2. And you can get these from the quadratic formula. Now there are three types of roots that you can get. The first type is real roots, like real numbers. This you get when b squared minus 4ac is greater than 0 over here under the square root. This is the one I'm talking about. The second possibility is a repeated root. Now this you will get when b squared minus 4ac is equal to 0. And lastly, we have the complex roots, which you get when b squared minus 4ac is less than 0. Now let me give you the general form of the solutions for each of these three possible types of roots. The derivation of these is not too complicated, like you can derive them by playing a bit with converting the second order differential equation into a system of linear equations and then using eigenvalues and eigenvectors. But you will end up with the following formulas. So for the first one, for our real roots, which we said we get from b squared minus 4ac greater than 0, and assuming these are not equal, our solution is of the form y is equal to b1e to the power r1x plus b2e to the power r2x. Now r1 and r2 are the roots here. The second possibility we said is the repeated root. From b squared minus 4ac equal to 0, then your solution is y equals b1 e to the power r1x plus b2 x e to the power r1x. Now r1 here is equal to r2. Here you can write r1 or r2 or just r, it doesn't matter. And the third one is the complex roots, which is b squared minus 4ac less than 0. You get two roots. Let's say r1 is equal to a plus bi, and r2 is a minus bi. Then your general solution should be y equals b1 e to the power ax cosine bx plus b2 e to the power ax sine bx. I want you to remember that these both always come as complex conjugates. The only thing different between them is this sign. Okay, and that's it. This is how you solve second order linear homogeneous differential equations with constant coefficients. Let me show you some examples of applying these formulas. So suppose you have y double prime plus 3y prime minus 10y is equal to 0. What we're going to do, the first thing is using our characteristic equation, which was ar squared plus br plus c equals 0. We want to find the roots. Over here, a is 1, b is 3, and c is negative 10. So our characteristic equation becomes r squared plus 3r minus 10 equals 0. If you solve this, you should be able to get 2 and negative 5. So these are two real roots, which means our solution should look like this, which is y equals b1 e to the power r1x plus b2 e to the power r2x. We end up getting y equals b1 e to the power 2x plus b2 e to the power negative 5x if I take this as r1 and this is r2. And we're done. It's just literally 2 steps. Find the roots and put them in the appropriate places in the formulas. Or you can say into the form of the general solution. Let me show you another example which will yield some other kind of result. So say we have y double prime minus 8y plus 16y equals 0. Again, using the characteristic equation, you have r squared minus 8r plus 16 equals 0. Put this in your calculator and you should get only one root, which is r equals to 4. Now we have a repeated root, which means our solution should look like this. So it should be y equals b1 e to the power rx plus b2 x e to the power rx. So substituting the r's, I get my solution, which is y equals b1 e to the power 4x plus b2 x e to the power 4x. And we're done. And for our final example, let's see some complex roots. So you have y double prime minus 2y prime plus 17y equals 0. Yet again, a characteristic equation, r squared minus 2r plus 17 equals 0. Now if I put this in my calculator, it shows me a big error, which means that this does not have real roots. I have to go to my formula, which is negative b plus or minus square root of b squared minus 4ac over 2a. Substitution gives me 2 plus or minus square root 4 minus 4 times 1 times 17 all over 2. Now a little bit of simplification. 2 plus or minus square root of negative 64 over 2. Now negative 64 is 8i. Divide everything by 2, I get 1 plus or minus 4i. Any point you guys get something different than me, let me know in the comments. So, for our complex roots, we said our solution should look something like this. Which is y equals b1 e to the power ax cosine bx plus b2 e to the power ax sine bx. Over here, this is a and this is b. Then my solution becomes y equals b1 e to the power x cosine 4x plus b2 e to the power x sine 4x. I'm done. But what if we had some initial values? What if we wanted to find b1 and b2? Let's see what happens. Now suppose I have y0 equals 0 and y prime 0 equals 1. I have these two conditions. If I'm able to implement these into my general solution that I found right here, I can actually solve for b1 and b2. Let's do that. So for our first condition here, everywhere I see x, I'm going to substitute 0, and then my y should also end up being 0. So for this one, I have 0 equals b1 e to the power 0 cosine 0 plus b2 e to the power 0 sine 0. I just substituted 0 for wherever I saw x and then equated it to 0 because it's right here. Now we know that sine 0 is 0, this gets cancelled. And cosine 0 is 1, and e to the power 0 is also 1. So I'm left with 0 equals b1. And there you go. We have one of the constants. Now let's try to use the second condition. But for that, we have to take the derivative of our general solution. Let's do that. The derivative of our general solution is b1 e to the power x cosine 4x minus 4b1 e to the power x sine 4x plus b2 e to the power x sine 4x plus 4b2 e to the power x cosine 4x. Now I'm going to substitute zeros for all the x's and equate it to 1. Then I get 1 equals b1 e to the power 0 cosine 0 minus 4b1 e to the power 0 sine 0 plus b2 e to the power 0 sine 0 plus 4b2 e to the power 0 cosine 0. Some cancellations again. Sine 0 is 0. Same thing here. We said over here that b1 equals 0. We have a b1 right here. So this term also is 0, and we are left with just one term here. Now cosine 0 is 1. E to the power 0 is 1. So we have 1 left here. So 1 equals this thing, which is 4b2. This tells me that b2 equals 1 over 4. And there you have it. You have solved for both of the arbitrary constants using some given conditions. Now I can substitute b1 and b2 over here. So substituting b1 will get rid of this entire term because it's 0. So I'll be left with y equals 1 over 4 e to the power x sine 4x. And that is my final solution.